All right, so now that we've given you some basic definitions about current, we're actually going to build up a model for how charge flows. And the simplest way we can think about charge flowing is just a lot of different charge carriers moving down a wire. Or if we zoom in, we can think of charge flowing through some tube. Now this tube is going to have some cross-sectional area. So this is the cross-section that we're going to call A. And within this tube, we have a lot of different charge carriers. And in this example, I'm going to use positive charge carriers. And they are moving down the tube under the influence of some electric field. So that is what makes them move. Now each charge carrier is going to be moving with some average velocity that we call Vd, or the drift velocity. So we already defined that we can think of our current as the amount of total charge, big Q, that flows down our wire in some time, delta t. So to figure out how much total charge is flowing, we first need to say, well, each individual charge has some amount of charge, little q. And in total, going down our wire, we have some small n, which is the number of our charge carriers per volume of our wire. So from this, we can start to write down what our total charge, delta big Q, is. That's just going to be the total number of charges per volume times the charge of each one of our charge carriers times the volume of our wire. So now we need to work on what our volume is. Well, if I zoom in and I only look at some chunk of wire right here, I know that that chunk of wire has a cross-sectional area A. And if I think of just one charge carrier traversing from one end to the other, I know that that goes through some distance delta x, which is equal to the drift velocity times however long it takes for it to go down that wire. So now we can fill in for our delta q, that's just n times little q, times now our volume we can write as the area times this delta x, which is v d times a delta t. So now we can actually write down what our current going through this wire is. Our current is our delta q divided by our delta t, which if I take our expression for delta q, that's just n times q times the cross-sectional area A times our drift velocity Vd. So this is now a simple way of thinking about charges flowing down a wire. But in fact, we can think of current in a much more general way. So if we want to think of, say, current flowing through a galaxy or current flowing in cells, we need a more general definition of what current is. And so we're going to define a new quantity called J, which is a vector. And this is what we call our current density. And this is then defined as our current per cross-sectional area. So if we think of this example, our J then, which is our current per cross-sectional area, we can just divide our I over here by our cross-sectional area A. And so in this particular case, it's just N times Q times Vd. Now the reason we want to define this J is that it gives us a much more general way to write down the current I for any geometry configuration of charges flowing. So we can just think now of our total current I as being the integral of this J dotted with the cross-sectional area A that it's flowing through, and we take this integral through the surface through which that current flows.